So let's look at this idea of polynomial division. The basic, algorithms, I think the official word for it, but for a division. Now, that's not just polynomial division, by the way. That's any number is like that. A divisor, so AX is a divisor, times a quotient plus a remainder. Now, in fact, I'm talking about polynomials here instead of numbers. It doesn't make a scrap of difference because a number is a polynomial. So that's why it is the same division result. A couple of notes though, where we need to take into account when we're doing polynomials, so we know when to stop. The degree of the remainder should be less than the degree of the divisor. So once you get that situation, we know, okay, stop, that's got to be my remainder. And also, well, kind of obvious, I suppose, but the quotient and the remainder are unique. That just means they're different things. Because if they weren't, well, you could factorise it, because they'd be the same thing. Here's one from a very old HSC paper. So find the quotients. I guess the main reason I'm using this as an example is to illustrate, hey, if you're doing a division, you're still putting the missing terms. So like you have a column for each of the pronumerals, so power of, in this case, 4, 3, 2, and so on. But polynomial division really is just the leading terms is all we're worried about. So x to the power of 4 divided by x squared would be x squared. Then we go and multiply. So we get x to the 4 plus x squared. And then we subtract down. And I get minus 2x squared. Bring down those other terms and start again. Minus 2x squared divided by x squared is minus 2. Multiply out. And I now have 3, but the degree of that, of course, is 0, and that's less than the degree of my divisor, so I stop there. So the quotient is x squared minus 2, and the remainder is 3. So let's go even further back in time. Let's do our division. Okay, 2x to the 4 divided by x squared, 2x squared. Multiply out, do our subtraction. Okay, we can go into 4x cubed, so we get 4x. Do a subtraction. No, we can still keep going. Minus 2x squared divided by x squared. And eventually you end up with a remainder of minus 1. Hence, write this. So basically, write it out as that algorithm. So there we go. We've rewritten it as the quotient times the divisor, and our remainder was minus 1. Let's talk about graphing polynomials, because essentially you get something like this, where you've got polynomial x divided by some other polynomial. By that algorithm, I could rewrite that as the quotient plus the remainder over the divisor. Why do it that way? Because this tells us a heck of a lot about the graph. Remember? The bottom of the fraction equals 0. That's going to find those vertical asymptotes. The quotient turns out to be the other asymptote. Now, it might be a horizontal one, it might be an oblique one. The remainder, that tells us, well, if we can make that equal to 0, if we can solve that problem, that'll tell us where it cuts the horizontal or oblique asymptote. So say I want to draw this then. So I've already broken it up, and so it's y equals x plus 8x on x squared minus 9. We know we have vertical asymptotes. Bottom of the fraction can't equal 0. So plus or minus 3. So let's draw those in. We'll have an oblique asymptote at y equals x. So there's y equals x. In this case, it is possible for the curve to meet that asymptote, because if I look at the top of the fraction, it is possible for 8x equal to 0. And that's when x equals 0. So I know the curve will go through the origin, which happens to be on that oblique asymptote. Now the reason we can do that is because oblique asymptotes and horizontal asymptotes really don't mean anything until you get out to infinity. It's telling you what happens out of the extremities. So around 0, it can cut it if it has to. Right, we know we have to bend towards the asymptotes. There it is. So how did I know this? Well, the triangle on the left had to be in here, because if it was in the other bit and bending towards the asymptotes, it would have to cut the x-axis. We don't have any other x-intercepts. We can't do that. Same on the right-hand side. Now, in between the two, I've really only got one or two choices. The one that I've drawn in, or the reflection of that. Which one is it? Well, it's just a matter of subbing in a point and seeing what happens. I can pick x equals 1, see if it's positive, see if it's negative. Okay.